let's say a couple things about last time, just to remind us. So last time we had symmetry defined via topological operators. U, G was an element of the symmetry group, and they could be put on any codimension 1 manifold, MD minus 1. And we also learned that networks of symmetry defects these operators are called symmetry defects, was just the same thing as flat background flat background gauge fields. So studying correlation functions in the presence of these defect operators is the same thing as just turning on a background gauge field for our system. And if G is discrete, if the symmetry group is discrete, we can really omit this term here.
Well, I can ask a question regarding this. So you mentioned a scenario where there was an S1 and there's a background holonomy around it, which could be thought of as a symmetry defect inserted across this, at a point on the circle. So clearly, as you pass that, you get to a G transform field, right? But is this continuously related to the previous region where it was not symmetry transform? So there was a what I'm saying is that from that point of view, it's not in some sense it's not disallowed to come back to the same point but with a symmetry transform. If that is so, then why can't I imagine a junction where you can come back to the same point but with the symmetry transform? In some sense, if you want, you can excise a small neighborhood, let's say near the junction, if you want. That would be a very similar situation to in this one in geometry.
Can you just repeat? Sorry.
So he mentioned a scenario where there was a holonomy of a background gauge field,
Yes.
which could be thought of as a defect positioned at a particular point on the circle. So as you pass through it, you get transformed by G.
That's right.
But now you are coming back to the same point with a G transform.
Once you come back not to the same. I mean, the rule is that as you cross the boundary, the field here and the field there are related by G.
Yeah, but now you can come back.
You can come back, but you don't come back to what you were here. When you go to the left and to the right of the boundary, there's a G transform there. That's a well-defined. This process doesn't not change the field.
Process.
It's not like what you are here is the same as what you are here. You evolve when you are here.
But that could also happen in that scenario.
So the rule is that the field here and the field here are related by G transform. It's like a chemical potential.
Right. But what I'm saying is that even in the case of junction, that could happen, right? That could be managed. That even if as you cross the
No, the rule for I'm
It's fine. No,
the
please.
rule for the junction is it's a question locally. Just on this side and this side, you have a well-defined rule. If this thing gets not away, you don't have a well-defined rule locally near it. It's not a question of what happens as you go around. That is the problem. I'm really.
It's fine.
topological, right?
Please.
So if you imagine excising a small neighborhood at the junction, then the situation is exactly the same. There's no notion of us.
It just seems to me that the rule is not well defined. If you don't, you want a rule for the fields here, here, and here. So the rule is that from here to here you do G1, here to here you do G2, here to here you do G3, and that should give you a well-defined closed rule. It seems to me.
That's what I think as well. But
Instead of a junction, if you just have one line with a G,
Yeah.
then clearly
No, you're not allowed to go around because you evolve as you go around. The rule is just from here to here. The rule is what happens just to the left and just to the right. That is a well-defined rule. Now you're saying that if you go around, you get a contradiction. You don't, because you evolve.
Because
You evolve as you go.
In the junction case, what you talk about is like error over thing, like basically. You can have error over things.
I mean, you have to define your rule. If the rule is that field here is G times field here, and you keep going, and you want a well-defined field configuration, then you can't go. Maybe it's something more you can.
No, but in the junction also you can evolve, right, as you move around.
No, but it's all local. Maybe this is what you're saying about excision.
Yeah.
Okay,
So
then
I think if you, it might be true that if you change the topology by literally cutting out a hole,
Yeah.
that you can do something different. But then you're literally changing the topology. And since the whole system is sensitive to topology, I think it would probably be okay.
Or if you allow, at least in the continuous case, non-flat backgrounds, then you might be able to concentrate
Yes,
curvature.
absolutely. Yeah, absolutely.
That's
Yeah.
what
Yeah,
I meant,
yeah.
That's what I meant, yeah.
Right.
Yeah,
Yeah.
but perhaps in the discrete case.
In the discrete case, you might literally have to just cut out a hole in the space-time. And then you've modified the topology, and then you can have a more interesting thing.
Anyway, it's clearly a different thing. This is completely a flat.
Okay, so we saw these two things, and then at the very end, I made a kind of claim that an 't Hooft anomaly was, on the one hand, failure of gauge invariance for a background field. And is, on the other hand, some kind of ambiguity when manipulating symmetry defect. Now I'm going to delve into this a little bit more, but just to emphasize, so the symmetry defects are topological. The fact that they are topological came about, if you remember in the continuous case, from gauge invariance, from current conservation. So this failure of gauge invariance will come about when we have some configuration of symmetry defects, and we try to move them in a way that looks topologically obvious, and we encounter some phase ambiguity, some problem in doing that. So we're going to see a couple examples of that. Okay, let's do an explicit example motivated by yesterday's lunch conversation. So the simplest explicit example is quantum mechanics. And we will have symmetry G, some unitary symmetry. So quantum mechanics means a 1D theory, so these defects are points. What kind of interesting ambiguity can we get? Well, so here will be our space-time. It's just a line. Actually, it needs to be shorter, so there's more room. And here we could put a symmetry defect G, and here a symmetry defect H. Okay, there's not much interesting topology going on here. The only thing I can do is try and shrink this distance. So I can try and combine them into GH. And so topological invariance of the defects would tell you that these should be equal. But in fact, there could be an ambiguity. The ambiguity is some phase e to the 2 pi I omega of GH. Okay, so let's allow for this possibility and chase it down and see what it means.
So, just there's something bothering me about the previous discussion that we had. So, as you go around, I don't understand what Shiraz said about the evolution and the field coming back to itself. Because I would have thought this is like a cut which makes the field multi-valued. In particular, if you go it around it n times, you will just get multiplied by G to the n. Right? If it were to come back to itself, then couldn't do that.
Yeah.
I mean, what would make it evolve in G space? They were just a cut.
It's like putting on a Wilson line.
Yeah.
You've got a charge field with a Wilson line. The boundary condition is the field here. As you go around 2 pi, it picks up a phase.
Right, so
Yeah.
it's multivalued, right?
Right, but the field here and the field here are always related by that phase.
Right.
And then you,
that is true.
then you turn on a momentum so that
But what I'm
maintained.
saying is that it's multivaluedness is allowed.
But from left to right there is a defined jump.
Yeah, so that could still be.
That's the nature of the
achieved.
multivalued.
That could still be achieved in the case of junction, where you, as you pass, you can get multiplied by G1. You can, as you pass, you can get multiplied by G2. As you pass, get multiplied by G3, but need not come back to 1. It can G1, G2, G3 can be not 1.
But that's a different rule. You've got a well-defined field configuration in the neighborhood of the junction, such that G1, G2, G3 then makes it 1. So that it's well-defined in the neighborhood of the junction. See, in the case of the circle, it's completely well-defined in the neighborhood of the junction. Now you may want a different rule.
No, I'm just trying to make sense of what would be a non-flat.
I understand, but that's a different thing to do.
Yeah.
I mean, maybe that makes sense.
I mean, we are building up this formalism as we go along, right? So why not include the formalism curved connection, where the curvature is concentrated?
I just don't think that, I don't know any mathematical notion of a curved discrete gauge field. So it could be this, but a priori, just from mathematics, there's no obvious thing to import. We might have to figure it out. Okay, so the simplest explicit example of an anomaly that is sort of realizing this discussion is that we could have we could be in quantum mechanics with symmetry G. So the defects are points, and the only thing we can really do is try and fuse them. And naively, we're just supposed to get that the fusion works. But here we could have a phase mistake. That's an example of what I mean by an ambiguity when manipulating the symmetry defects. So we can try and constrain this phase. Okay, so we would like it to be associative. So if I put a third thing here, I don't want it to depend on the order. So I get some equation. Like this. This is all mod Z. Yes, indeed. So, but that was just from demanding that the phase is well defined. It doesn't depend on the order in which I close things off.
Sorry, what was the logic for saying that the only thing that could happen is a phase? I mean, is it the usual logic of quantum mechanics that phases are not measurable? Is that the idea?
Isn't it that you jump by, this defect causes a jump, right? So you jump by G and then you jump by H. And if they come together, when you cross both, you still have to jump by GH.
Mm-hmm.
But I guess in quantum mechanics, yeah, you might have a phase. The wavefront, but this is time, presumably.
This is time indeed because it's quantum mechanics. Yeah, but more generally,
The logic being that, is this, the usual logic of projective representations in quantum mechanics is that you don't need to implement group symmetries. Faithfully, you can implement them up to phases. Phases are not measurable. I'm just wondering if that's
I guess in this particular case you can use that logic, but
that phases are not measurable.
the reason I'm hesitating a little bit is that in later examples where it will not be so obvious how it is related to some action on a wave function, I will still want to assert that the ambiguities are phases.
So then what is special about a phase? Why should it be modulus 1?
Yeah.
And why not the full operator? I mean, yeah.
I think so. Good. So yeah. So the main thing is that when we discuss an anomaly, it has to do with the. You remember the distinction I was making between ABJ anomalies and here 't Hooft anomalies yesterday. So we want the violation of when we say that a theory has an 't Hooft anomaly, we mean that the violation of current conservation or gauge invariance is by a C number, by some multiple of the identity. If it were a violation by an operator, then it would depend on other insertions. And more generally, there's actually an argument that you can always remove such things. Roughly speaking, if you have an operator violation, you can just include a source for that operator and modify the gauge transformation to include shifting that source as well, kind of like Green-Schwarz. So the first thing is that when we discuss anomalies, we really mean that the violation of gauge invariance is by a number, a multiple of the identity. And then we should say, why should it be modulus 1? Let's see if I have a...
Can I ask you something? Shouldn't the action of G and H each individually keep the modulus of the wave function fixed? Usually, and that's unitary representation, right? Because suppose it didn't, you can always define a new action where you don't change the modulus. That's sort of the...
Yeah, the symmetry operators are supposed to implement the symmetry unit in a unitary way. Yeah. Probably that nailed it down to be a phase. Yeah. But so the fact that it's not an operator here, that also has a good answer. If there were an operator here, just imagine including, instead of a multiple of the identity, imagine including in the action a source for that operator.
In the action of the field theory.
Yeah, that's right. So instead of having just a background gauge field for G, I'll also have a background source for this operator that showed up here. And now I'll change my rules for gauge transformation. I'll say that under this is supposed to be a gauge transformation, this fusion of the background G gauge field. I'll also say that under that gauge transformation, the source for this operator changes in such a way as to absorb that operator.
And that can always be
done. Yeah. Yeah. So there aren't in the slogan is that there are no operator valued anomalies. They're always numbers. Always multiples of the identity. Okay, so we get this equation on this.
Explain the equation again.
Oh, this equation just came by, imagine you put a third thing k, and you just demand that it's associative. So you demand that this phase is well defined, essentially. So then you get this equation. So as was anticipated by someone in the audience, this is a co-cycle condition. And now, I mentioned yesterday that we're only interested in anomalies as equivalence classes, in the sense that I might try to redefine things to remove an anomaly. How would I do that here? Well, I could just change the symmetry defect G to e to the 2 pi I eta of G times G, where G, this is some phase that depends on the defect. And if I do this, I'll find that omega of GH will change to omega of GH plus eta of the product minus eta of G minus eta of H. And this combination, this kind of term will always satisfy this equation. Have people seen that before, or you believe it? Okay, you believe it. All right, so the equivalence classes of omega that you get this way are elements of the group cohomology, H2 of G with coefficients in U1, and such thing defines projective representations. G.
Sorry, I'll just reveal my extreme ignorance and ask you to translate that to English.
This thing?
Yes.
Okay. I literally defined it for you. So an element of this group cohomology is a function that takes two elements of G to U1, like this here, subject to this condition.
So the group to U1 that implements the group algebra, basically.
That's right. So subject to this from two copies of the group. So it takes two arguments, G and H, to U1, subject to this condition, and the fact that we're in cohomology means that we mod out by maps of this form.
Okay.
So it literally just the definition was up here.
So this is just a name.
That's right. It's a name for what we encountered. And it's known to define projective representations.
So now this is somehow related to the topology of the group.
So good. So if G is continuous, this is closely connected to pi 1 of G. So the possible things that can, so for instance, if G is simply connected, there can't be anything. If G is discrete, it's more interesting. There's no other way of defining it than by computing these functions. And that's not such a bad thing to do if G is, say, Z2 or whatever. It's,
Related to Durham cohomology?
Durham cohomology? No. So for instance, a projective representation, so the two-dimensional representation of SU2 is a projective representation of SO3. That's sort of the most familiar physics example.
And just to understand this in this language, so that means you take two elements of SU2, I presume, and you try to map them to U1. Is that
Two
somehow?
elements of SO3.
So the two-dimensional representation is an honest representation of SU2. There's no
So
phase
there are
ambiguity.
two there.
Representation of SO3 lifts to a.
Yeah, that part I understand, but I was trying to relate it to the definition you gave here, where you took two elements of the group.
That's right.
mapped
So
them to U1, and so there are two. Sorry about this. Go ahead. Please.
yeah, so imagine we take SO3 elements and we try to force them to act on the doublet.
Yes.
Okay. So we try to multiply them, and we'll find that the representation, the multiplication will almost work, but there'll be some phase problem. There'll be some phase that we're off by when we try to multiply them. That's how we define this in that case.
So it's not just a property of the group, it's a of a genuine representation of the group. I mean, you also have to talk about representation when you define group cohomology.
The group topology matters.
These different things classify different projective representations. So the elements here classify different projective representations.
So there is one representation in which the half integer spins of SU2 lie, and another representation in which
Right. So if we did this for SO3, we would find that for representations of integer spin, the class would be trivial, and for representations of half integer spin, it would be non-trivial.
Roughly half of the group would map to 1 and half would map to -1, something like that.
No,
Half of the rep.
yeah, I mean, well, you have to deal with this and so forth, so there's a little bit of ambiguity that's up to you. But yeah.
It's more where the G times H is mapping to
That
one.
much, right.
Yeah. Okay. So okay. So
It's 2 pi or 4.
Yeah,
0 to 2 pi.
whether the product
Rotation is the rotation by 2 pi over 0.
Half of the universal coefficient.
so in quantum mechanics,
So sorry, just to
yeah.
ask, because this word is used all over now. This is all group cohomology. Suppose I never learned.
yeah. Group cohomology is an extremely simple thing. So this is the first instance of non-trivial group cohomology
Okay.
group. But more generally, it's just you take functions on the group,
Okay.
obeying some constraints, modulo some equivalence relation. So functions of many copies. So so H3, which we probably won't encounter, but we could, takes 3 elements of the group to whatever sits here,
I see.
subject to some equation that looks like this, modulo something that looks like this.
Thank you.
It's a very
I'm going to have to
okay.
catch you.
Yeah. So it's a very explicit thing, and for discrete groups, it's just some little calculation to work out what these things are, because there are some few arguments that can go there, so you can just write down all the functions.
So I have a question from the signal physics, which is that the notation is quite similar to Durham cohomology as well as to the cycle cohomology of cycles, the things which are closed but not boundary of something else.
Yeah. So I mean
Is there a relation?
well,
Formal relation.
yeah, formal relation.
Those are yeah. This is
So far it's we just take this as the same notation.
just take it as the same notation. I mean, mathematicians tend to denote all things that can be defined as some class of things that are closed modulo some class of things that are exact in a similar notation. So this is in that spirit, similar. Okay, so good. So what's the physical consequence? So first of all, we learned the following slogan. In quantum mechanics, unitary symmetry, or anomalies for unitary symmetry, is the same thing as projective, saying that the Hilbert space is in a projective representation. And since it matches on all scales, as we discussed, anomalies match as we go to lower and lower energies, the physical consequence is ground state degeneracy. So not only is the Hilbert space in a projective representation, but the ground states are in a projective representation.
And sorry, just say that again. So anomalies for you, when you say anomalies, you mean it now in quantum mechanics in the same sense as you meant yesterday?
That's correct. Yeah. So I was so this is a right and for quantum mechanics with the symmetry G. Let's say it in all the different languages that we can. So in quantum mechanics with symmetry G, we could first of all before talking about symmetry defects, we could just couple to a background G gauge field. G could be U1, G could be Z2, whatever. Okay. And now we could try and do a gauge transformation of the background field, and we might find that the partition function, say on a circle, is not quite gauge invariant. And that's an anomaly, that not quite gauge invariance. We can also rephrase the same thing in terms of symmetry defects and some failure for the correlation functions of symmetry defects to be exactly topological, and that failure is this phase. And then once we know that, we can try and classify what are the ways in which it can fail. So we can classify the omegas that can sit here, and then we can deduce what is the physical implication of saying that. So I want to stress.
I'm really sorry.
Yeah.
But the link I'm missing is why does the anomaly defined in the first way as a failure of the partition function to be gauge invariant vis-a-vis a background gauge field imply a non-trivial phase here and vice versa?
Good. So the first thing is that there's a complete dictionary between symmetry defects and flat background gauge fields. Every flat background gauge field is some configuration of symmetry defects. If we're talking about quantum mechanics on a circle, it's more obvious in the sense that all that we can do is put some holonomy. We can put some sequence of jumps. And here I'm putting some sequence of jumps. So I'm describing for you, by putting some various things here, the most general flat background gauge field that there can be. The next thing is that the fact that the defects are topological, that you can move them in any topological way, is equivalent to the statement of gauge invariance for the background field. Remember, we saw that explicitly for the U1 case, that when we try to move the manifold that it's on, we come up against current conservation, which is what implements gauge invariance.
Okay, beautiful.
Yeah. So that's the dictionary. That's the link between them.
I see. And then to the extent that you can't move them past each other, that's like in the continuous case, d mu j mu is f of a, right?
Is something, yeah. So, some obstruction to finding that d mu j mu is 0.
But it almost relates the phase to the.
It should. That's exactly right. It does relate the phase to the divergence of the current, which does give you the anomalous variation of the action. That's exactly right. Yeah. Yeah. Okay. So what happened here? So the physical consequence of this is that we get ground state degeneracy that is protected by symmetry. So if we have a quantum mechanics with symmetry G, and it has an anomaly, the ground states have to be degenerate. That's because the basic reason is that projective representations have to be at least dimension 2 or greater. There's no projective representation of dimension 1. Right here we saw, for instance, the doublet. So we learned that if you have an anomaly, the ground state is degenerate, and it's protected by adding interactions, adding interactions that preserve the symmetry. You can't get rid of it.
Sorry, isn't the identity representation a particular trivial case of predictive representation? And other cases zero and everything is.
Yeah. So if we want this to be non-zero, so here, if we want the class to be non-zero.
Who told you the ground state transforms in the non-zero representation?
So if this element is non-zero in this cohomology group, then the representation is non-trivial, and in particular, dimension larger than 1.
Oh, you're saying the entire Hilbert space transforms to the same predictive representation?
Yeah.
Same phases?
Yeah.
I see.
Sorry, I mean, so in this particular case of SU2 and SO3, the ground state could be a doublet or a triplet in particular, or a singlet. So is this it necessarily that it has to be a half integer spin?
Yes. So half integer spin, if G was SO3, and we found that the theory had an anomaly, a non-trivial thing, then a non-trivial class here, then everything would have to have half integer spin. Because the integer spin ones have trivial class here.
Sorry, I thought H2 just tells you which kind of classes there would be. Either there would be trivial class or
H2 tells you which kind of classes there are,
okay.
but a particular theory realizes an element omega.
Oh,
Right?
Yeah.
Because we do this calculation. This is a calculation that we do in some fixed theory, and we get a particular omega that comes out. This tells you where omega lives. Omega is some element here, but the theory gives you a particular omega.
it's not state dependent.
It's not state dependent, right? This doesn't know about any state. Right. Yeah.
Is
Good
Kramer degeneracy an example of this?
Is Kramer's degeneracy? Yeah, Kramer's degeneracy is an example of this where you don't do unitary symmetry, but you do anti-unitary symmetry. In fact, I'll maybe do an example related to that in a minute.
And there is time reversal, is it?
Yeah. You could do the same thing for time reversal, and then Kramer's doublets are an instance of this. They're doublets that are protected by the symmetry. So any interaction that preserves the symmetry preserves the doublet in the spectrum. Good. So, okay, so let's actually do an explicit model that has an anomaly. So we can see with our eyes a little better. That's sort of the nature of this stuff, is that the formalism looks extremely slippery and abstract, but when you do it in practice, it's a little easier. Okay. So here's an example that everyone likes. Particle on a circle. Okay, so what's the Lagrangian? Well, I have a standard 1/2 q dot squared, but q will be on a circle. So q is identified with q plus 2 pi. And then because of that, we can add an interesting topological term, which is theta over 2 pi q dot. This is a total derivative. So this coupling theta is some parameter in 0 to 2 pi. Okay, so good. So let's look at the energy eigenstates in the spectrum. Okay, everyone has done this problem before, so I'll kind of leap to the answer. So the energy eigenstates are labeled by some integer n, and well, the wave function is just what you expect. So the wave functions are 2 pi periodic, and the energies of these states are that. So n is in z here. Okay, so that's the solution. Okay, there are two interesting, well, let's actually plot the energy eigenstates just to make things even more clear. So this direction will be E. This direction will be theta. Here's 2 pi, 0, pi. Okay, so if we start at 0, so it's clear from this formula that when theta is 0, n equals 0 is the ground state. N is isolated. So there's a ground state here. And then the excited states are degenerate because theta is 0. So they're degenerate with n and minus n. So here we have 1 and minus 1. And up here we have 2 and minus 2. Okay. Now we plot this as a function of theta, and interesting things start to happen. So we get something like this, and let's see if I can get this correctly. This should come down to here. So at 2 pi we should get back to ourselves, but the interesting thing is that there'll be some level crossing. So this goes up, down, up, and down, something like that. Oh, I missed my mark pretty badly here. So it should come at the same point. It should come. Well, this is all supposed to be at pi. Okay, something like that. All right, so what's happening? So look, something interesting is happening at theta equals pi. First of all, the ground state is degenerate, and every state is degenerate. So here at theta equals 0 versus theta equals pi, something interesting is happening. And now let's try and explain it. Is there a question? Yeah. Okay. Good. So there are two symmetries that we want to focus on. Two Z2 symmetries. Okay, so one of them, let's call it X. This sends Q to Q plus pi. This is actually a symmetry for all theta. Now let's call the other one Y. Y sends Q to minus Q. This is a symmetry only at theta equals 0 and pi. At theta equals 0, it's obvious that it's a symmetry. At theta equals pi, we need to use the fact that we need to use the identifications here to see that it's a symmetry. Okay, so let's look at what happens when we consider xy versus yx. Okay, so xy on q is x on minus q, which is minus q plus pi. And yx on q is x on q is, so it's y on q plus pi, which is minus q minus pi. And again, because of the identification, these are equal. So xy is yx. So in general, acting on all operators in the theory.
Why do you pick GQ minus Q plus pi as a symmetry and not?
So there's a U1 symmetry where you shift by anything. I'm zooming in on this because I will later break the others. Right. In general, yeah, indeed, there's a shift by anything that's a symmetry here, and there's this at the special values. But let's just zoom in on this Z2 times Z2 because that's all we'll need. So acting on all operators, xy equals yx.
But considering the subgroup of the symmetry is slightly tricky, right? Because sometimes you may end up concluding that it's a projective representation, but if you consider the full set of symmetries, it may not be. Why is it okay to consider the subgroups to keep track of all?
Is that really right what you said? I think if it's projective on a subgroup, it's projective because what we're ultimately gonna find is a violation of this relation. This relation is still true in the group itself, so I think it's sufficient. Okay, so
So acting on all operators, yeah, okay.
because we checked it on Q and Q generates all the operators. Okay, so okay, now how do these symmetries act on states? So x on n, well, that's easy to check because we just shift Q by pi. This is just minus 1 to the n on n. Okay, what about y on n? So y is the symmetry that's responsible for the degeneracy. So y on n equals minus n if theta is 0. That's what we need to make the spectrum look degenerate there. But it's minus n plus 1 at theta is pi in the labeling scheme that I've chosen. So yeah, I think that's correct. So you can see how these lines come to meet, and you'll come to that conclusion. Okay, so now,
Sorry, I know there should be elementary, but at least in the wave function you wrote down, which was true for all theta, isn't it e to the in q?
mhm.
If I literally, so you said the action is not just q goes to minus q, it depends on theta, isn't it? I mean, if I naively took that wave function and I set q to minus q, I would have still said n goes to minus n.
Let's see, that can't be right because at theta is pi, those states are not degenerate.
When you shift it by some arbitrary, I mean, this contains the information about the phase, I guess, minus n plus 1. Minus n plus 1 is presumably related to n by some phase. So for generic values of theta, I think q going to minus q will become some theta dependent phase. Is that correct?
Yes. Q going, sorry.
The y operation will. So this comes with the phase convention. Your wave function already comes with phase convention.
Yes.
So, however, the representation of y could give you some phase. Is that right? I mean, I'm trying to see how otherwise minus n. I mean, I have the same question as
Yeah.
minus n plus 1. Is it related to minus n?
The wave function should be decorated with the theta phase. So that
Okay, let's see if we can figure it out. So
spectral flow.
So the thing that I wrote was this. Right, but I also need, but I chose this for all thetas. If I want to write wave functions that have theta dependent, that implement the spectral flow, I'll probably need to give them a theta dependent phase, as Abhijit suggested. And then, what will it be? It will be, yeah, something like this.
Such that then.
So if theta is pi, is this right? So maybe minus, I'm not sure, plus or minus here. So if theta goes to theta plus 2 pi, I'll, no, this is not.
No, I
No,
think
no,
it
no,
should be
no.
something linear in Q,
Yeah,
because
yeah.
it's like a
Yeah.
it's like a magnetic field that's put in. So it's a you have a quasi-periodic boundary condition. Yeah, something like
This
that.
like more like this. Yeah.
This is what will also explain the spectrum now in this thing, because it will be n minus theta by 2 pi whole square. No, so there is another way, so this is the quasi-periodic representation. So e to the power nq, that's a quasi-periodic representation. You can make it, periodic by putting this thing so that the energy now becomes just n square. I mean, the new n square.
No, but let's not, okay, all right.
Yeah.
I thought when you did it, you said, look, the conjugate momentum has to be d by dq, and,
No, the momentum. So the Lagrangian was.
d by dq is equal to q dot minus
q dot.
So
And the conjugate momentum is q dot plus some theta. And this conjugate momentum has to be minus I d by dq or whatever.
yeah, exactly. That's what I did. Yeah.
And therefore the wave function was e to the I n q.
That's what I did.
But the
Yes.
the energy spectrum was n minus theta over.
That's exactly what I did.
Yeah.
Just by rewriting this in terms of this.
But there's a canonical transformation which takes q plus q theta by 2 pi whatever. That this is this usual thing of shifting the quasi-periodic boundary condition to periodic boundary condition by shift of the.
Yeah, I made a convention where when I omitted this, I said my wave functions are exactly periodic, whereas I could have said that the theta term is implemented in a boundary condition on the wave functions, which is I think what you're doing.
Yeah, that's what I'm saying.
Yeah.
And in that, because in your old convention, minus n plus 1 is hard to see.
Yeah, I mean the only way to from plotting the energy eigenvalues, it's clear that that's what it has to be. But I guess you're right that if you wanted to see it on the wave function, you should include the theta phase that implements the spectral flow. Okay, so if we accept this slightly mysterious formula, we can now compute x, y on n and compare it to yx on n. So, well, this gives us x on minus n plus 1, which is minus 1 to the n plus 1 on minus to the n plus 1 on minus n plus 1. Whereas yx on n is minus 1 to the n times minus n plus 1. So you see this pesky plus 1 here. So xy on the states equals minus yx. So this is an instance of a projective representation. The algebra of the symmetries that we found when looking on the local operators is modified by a phase when looking on the states. And notice that the phase is central. It's the same phase on all the states.
It's weird. We didn't have to be.
Didn't have to be the.
Computation that this would be same for all there easily being a minus 1 to the n plus 1. So
That's part of what it means for it to be an anomaly, that it will be the same on all the states.
why not manifest? Seems like it could depend on the state. Maybe it's fine. Back off.
Seems like it could depend on the states. Well, it's part of what when the discussion that we were having with Shiraz when we were saying that the failure of the composition is by a phase that's operator independent. It's some overall multiple of the identity. That means that when the dust settles, it will come out to be the same on all the states. Okay, so this is symmetry protected degeneracy, which you might have learned can't happen in quantum mechanics when you took your first course in quantum mechanics. In particular, it's protected under adding any interaction. I mean, this was a free theory, but we could add any interaction that preserves x and y. So we could add some potential that.
Sorry, can I just
Yeah.
understand? So at theta equal to 0, the operator composition is implemented faithfully?
It's correct. Yeah, you won't find this sign.
And at theta
Yeah.
equal to pi?
That's right. Yeah. So something very special is happening at theta equals pi. So we could add some potential, v of q, that's an arbitrary function of, well, let's write it this way, v of cosine of 2q, for instance.
Sorry, if the operator algebra of defects was like that, then why the operators implement a faithful representation in states? In operators, would insert an operator and then also undergo this phase change because it doesn't really care about an operator. It just does this algebra on its own.
Well, I don't know, I don't precisely understand the question, but let me say that the whole kind of meat of what's happening is that on all the operators in the theory, you get this, but on the states you don't. So whenever you have, when we define the symmetry group, for instance, one question you might have asked is, why didn't I just define the symmetry group to be whatever this group turns out to be? And the reason I didn't do that is because the way I like to think about what the symmetry group is it's what acts faithfully on the operators in the theory. So we first, you remember we introduced the defects by saying that they act on operators. So here, when we checked this relation on operators, this is part of me asserting that we should take the symmetry group to be Z2 times Z2, because on the operators, this is what's realized. And then on states, we find something else. So the situation when we have an anomaly in quantum mechanics is always that on all the operators, we find one particular group, but on all the states, we find something else. So we could have, well, yeah, let me just leave that. So as I was saying, this is protected by symmetry. So if you make the model more interesting by adding some complicated interaction like this preserves these symmetries. So it will preserve the ground state degeneracy.
Why is it clear that it would preserve the homology limit?
The what?
Group homology limit.
The group cohomology limit.
Element.
Oh, because it preserves the symmetry.
But it could change the element of the group homology.
Oh, no, sorry. Oh, I see what you're asking. You're asking why. Yeah. Yeah, okay, I see what you're asking. You're asking why do well I mean this is rigid, and you could add this with a tiny coefficient. Yeah, the anomalies, that's another virtue of them, is that I didn't mention, is that these cohomology groups are discrete, typically. They're integers or something like that, or torsion groups. So whatever you find here is rigid under continuous deformations. So cranking up potential is one continuous deformation. Yeah, it's an index type argument. Okay, so yeah, so this is supposed to be interesting and a little bit grating against your intuition from quantum mechanics that, you know, if you draw the double well, there's not supposed to be any protected ground states. And it's because that example is a little bit misleading, actually, because Z2 doesn't have any projective representations. The first interesting group that has projective representations is Z2 times Z2. So it actually is correct that the double well example is correct. But once you get to Z2 times Z2, roughly speaking, half the time there's symmetry protected degeneracy. With Z2 times Z2, it could have happened. That's right. You have to. There's a calculation to do.
Events are suppressed for the right objective
Yeah.
representation.
Yeah, so I mean, I haven't worked through this calculation, but I think what happens is that at theta equals pi, various instantons that you might conceive of have kind of signs that come with and cancel each other. But I haven't worked through that. Okay, so let's discuss some.
So really you're saying such a problem with the quadruple well would have this,
I mean, I think if you just do scalars in a quadruple well, it probably doesn't. You might have to do something a little bit more interesting. But in general, a model like that with Z2 times Z2 symmetry, you'd have to check. There's something to check. It could have symmetry protected ground
because
states.
give them the flavor of this theta angle and the connection.
Well, this is somehow the interesting part. This is the thing that is making things. But I won't be surprised if a small modification of the quadruple well has that Z2 times Z2.
How can I know the anomaly just by looking at the
Good. That's an interesting question. You're asking for the analog of the triangle diagram calculation. That's right. So one of the exciting things that I think is interesting about this field is that isn't known. So we're kind of at the state of the art, which I was going to talk about right now for a minute, is that we sort of kinematically know, we think we kinematically know what the possible anomalies are. But we actually don't know which systems realize those anomalies, and in general, what is the physical significance of all of them. So this one had a particular physical significance, the ground state degeneracy, the projective representations. But there's a lot of interesting physics to do. In some sense, a big math problem was solved, but the physics is still open. So let me just say that a little more formally. So it's convenient.
And sorry, since you said it, the big math problem to solve is that we now know all the group cohomology structure very well.
Yeah. Let me. I'm about to say it.
Oh,
Yeah.
sorry.
So it's convenient to encode anomalies by inflow. So that means we consider a d+1 dimensional non-dynamical bulk. And which should also be topological. So non-dynamical means, as per the discussion we were having yesterday, nothing is fluctuating. No sums are done. It's just some classical action. So, for instance, so the picture is that, which I'm sure you're all familiar with, is here you have some bulk, and in the bulk we have some action, some local topological action. This depends on the background fields of our problem. For global symmetries. So the lingo is that this thing here is it's invertible or an SPT. And if we had this on a closed manifold, it would be completely well defined. But since we put it on a manifold with boundary, some edge modes live here. Invertible, the meaning of that is that the partition function is a phase. So this is a math term. This is the condensed matter term. Yeah.
Math term for once.
Yeah.
It's clear.
Yeah. Yeah. Right. I should stress it's a phase on any closed manifold. So partition function on any d+1 manifold is some phase. Okay. And here, since we put it on a manifold with boundary, there's some edge modes with an anomaly. So the math problem that we, first let's say in the quantum mechanics example, how do you do this? Okay. So the bulk should be some 2D action. And you can write it like this. So we take our omega and we plug in where we had G and G, essentially two G gauge fields, G and H, and we integrate. So these are G gauge fields. I'm being slightly mathematically imprecise here. I'm happy to be more technical for those who care, but there exists a precise action that is roughly this.
So when you say omega, you mean it's bilinear in the
Yeah, remember omega depended on two group elements. So I can use that dependence to promote it to a function of two background gauge fields, and then integrate it over some two-dimensional bulk.
So we will be obtaining this quantity from D plus 2 dimensions, this gauge invariant object.
So in continuous anomalies, we often discuss things called anomaly polynomials, which are formal structures that exist in D plus 2 dimensions. And then we go down one dimension, we get to the thing that I'm talking about, and then we go down one more dimension to get to the anomaly. In general, the D plus 2 dimensional perspective does not exist. The thing that exists universally is the one here in D plus 1 dimensions.
If you have bulk, so reversing this, if you have bulk whose partition function is just a phase, molecular manifold, what exactly goes from an open manifold?
So a good example to keep in mind is Chern-Simons theory. So you have ADA. That's fine on a closed 3 manifold. But if you do a gauge transformation, if the gauge parameter doesn't vanish at the boundary, you're going to pick up some boundary term.
But this is a real gauge symmetry, right? You are talking about global symmetry.
Yeah, I'm talking about a background gauge transformation for a background gauge field. If that background parameter doesn't vanish at the boundary, then you pick up some gauge non-invariance there. That's the chiral anomaly for, say, a chiral boson. Okay, so what's the working hypothesis?
Sorry,
Yes.
maybe you already explained this, but the reason in Chern-Simons theory this works is that the action changes by a total derivative under gauge transformation.
Yeah, that must always be the case because this thing that I defined is completely, this S is completely well defined on any closed manifold.
Oh, you are inputting the fact that it's the action changes by a total derivative.
If you like, because I'm demanding that the bulk is something that's well defined on any closed manifold. And then it can only have a problem on a manifold with boundary. Okay, so the working hypothesis is that anomalies of d-dimensional quantum field theories are mathematically the same as this inflow picture suggests as d plus 1 dimensional SPTs. And when I say that there is a math problem that's solved, what I mean is that this side here is completely mathematically understood. Meaning, if I say I'm interested in 17-dimensional SPTs with symmetry group time reversal times SU2 times Z4, there's a crank you can turn, a kind of cohomology problem you can do to find all the things that can be there. So there's a kinematic classification of anomalies. We know where they can be valued if you believe this classification.
So that's also second group homology.
No, it gets fancier. It gets fancier. Depending on the dimension, it gets fancier depending on the dimension and depending on the symmetries in your problem.
I thought the previous discussion quantum mechanics was general.
That was general, but the reason it will get fancier is that there can be, in higher dimensions, there can be gravitational anomalies, and then there can also be mixed G gravitational anomalies. And saying what those are is a little bit fancy. But morally speaking, that's what they are. So the group cohomology is always a part of the answer, but it's not always the whole answer.
Second group homology would be part of that.
No, higher dimensional group cohomology.
But this defect algebra seems like a second group homology.
That's second group homology, but we'll find some other kinds of mistakes, not only this fusion.
Having to do with
Other more complicated manipulations that we might do in higher dimensions.
Because here the motion was only in time.
That's right.
So
Yeah.
there could be oblique stuff
Right.
in the higher dimension.
That's right. Okay, so
even working with codimension 1 defects.
even working with codimension 1 defects, the anomaly will the kind of cohomology group that it will sample will go up. It will go from H2 to H3 to H4, et cetera, as we go up in dimension. That's why they get kind of more interesting and harder to figure out what they mean.
But just to understand, if we were, say, just thinking about discrete groups, then these, in a sense, also include some discrete subgroups of diffeomorphisms and so on. I mean, is that
The gravitational part that you had in mind?
Yeah.
Yeah, so for instance, they're like global gravitational anomalies. So here's an example that I'm trying to understand. So there exists, according to this classification, there exists a discrete gravitational anomaly for 4-dimensional quantum field theories, which is Z2, which no one has ever encountered before. And the hallmark of this gravitational anomaly is that if you put your theory on CP2, CP2 has a large diffeomorphism, which is that you can complex conjugate the coordinates. That's a map from CP2 to CP2. And the partition function either can or cannot change sign under that transformation. That's the anomaly. So what does that mean? So this is what I mean when I say there's a lot of physics to be done here. You can look at this side. You can work out what these elements are, and then you can say, well, hey, this says that a 4D field theory could have a Z2 gravitational anomaly. What's that? How would I calculate it? Which theories have it? What does it mean? So there's a whole slew of physics to be done, to be mined from this.
Matter of considering global diffeomorphisms of a particular map. In particular, if you consider T4, 4D theorem T4, there's going to be a self-4Z anomaly, which one has to figure out. Clearly, it wouldn't be invariant and the model is invariant of the 4 totals. CP2 is a manifold with a smaller diffeomorphism group.
No, not all large I mean, that's part of the. This tells you that some large diffeomorphisms don't have anomalies. This answer. Yeah. So I'm happy to delve into the math of that more. This is a pretty interesting object, but from my point of view and from the physics point of view, I think it's interesting to sort of take things from here and try and figure out what they mean. It's like if someone told us that all possible anomaly polynomials in the universe are given by these 6 forms, but no one had yet computed any triangle diagrams or seen in general why fermions have the chiral anomaly. It's sort of that stage of development. So we have little bits and pieces. Okay, so we have to cut off at 11:30, right? So I think I will do one additional example, and then we'll start a new topic next time. So let me do one additional example.
Sorry,
Yeah.
to make sure I understand. All these statements are about discrete groups, right? And are the continuous anomalies in particular can be thought of?
Yeah. Yeah, they're in
the
there.
motion same as our usual notion of triangle diagrams?
Yeah.
And the higher
Yeah.
polygon diagram?
Yeah. I mean, in the sense that
These triangle
over
diagrams
here, for instance, I
are
keep
valued
mentioning.
in the group homology?
What?
These triangle diagrams are valued in the group homology?
Yeah.
Okay, maybe you can explain.
I'll be happy to explain that in complete detail to you. But let me actually get through one additional example. So
I'm really
Yeah.
should, of course, but just quickly, in case the bulk had this, the D plus 1D case showed that there is an interesting phase or anomaly, so to say. Usually are the physical implications then that if you had a boundary, you have a certain degeneracy or a certain,
good. So right. So that's really the question that I mean when I say there's something physical to mine. Is that what is? So I pick something here. I'm going to do one that's that's not that's not a projective representation, and we'll see what the physical implication is. So it'll be sort of more elaborate, but some particular physical implication. Okay, so let's now, we did quantum mechanics, so let's do a 2D QFT with symmetry G. Okay, so let's look at the following picture. So these are all, so the symmetry defects are lines. Okay, so we can consider a junction like this, and we can try and compare it to something where I slide H over here, this sort of standard F move. Okay, so topological invariance would try to tell us that this is the same, and we should now anticipate that in general we'll be wrong by a phase. So instead of getting equal on the nose, we'll get that it's equal times some phase. Okay, and now you do a song and dance like we did before. We check that it's consistent and so forth, and we find that this omega ends up being some equivalence class of this omega is in the third group cohomology with coefficients in U1. And the meaning of that is, again, that this omega is just some function of three group elements that takes us to U1, that obeys some equation, and we mod out by something. And the equation is qualitatively similar to what we had before. Okay, but what does it mean? So this is an anomaly that we can have. What does it mean physically? Okay. Hmm?
You could have a theory which also realizes the H2 combinations just on the same theory.
You can have an extension of representation. Yeah, I'm doing one that's not like that. Yeah, because this is sort of more. This is something that's intrinsically two-dimensional. We already saw the other case. Okay, so what does it mean? How will we answer this? Okay. So let's do the simplest case. So say G is Z2. So H3 of G with H3 of Z2 with coefficients in U1. Again, I stress that this is just some fancy thing for these functions. You can just work out what this group is Z2. So there's an anomaly that's either on or off in any 2D theory with a Z2 symmetry. So let's try and figure out how to tell if it's on. What does it physically mean? Okay, so here's a Z2 defect. Okay. So you can think, for instance, that there's some set of spins over here. They're minus, and then we've toggled them to be plus over here. Okay, so I claim, independent of whether or not we have the anomaly on or off, I claim that this defect, which is some quantum mechanics, after all this is some line in our system, defect quantum mechanics has time reversal symmetry. Okay, who ordered that? That's pretty weird. The bulk doesn't have T symmetry. And we're talking only about some unitary Z2 symmetry. So where can this T symmetry really come from? So
anti-unitary.
An anti-unitary time reversal symmetry. So this quantum mechanics has some anti-unitary symmetry on its spectrum. How does that come about? Well, so if you do a Z2 transformation in all of space-time, it doesn't preserve this configuration because it changes the plus and minus, for instance, that I was discussing here. But there's another symmetry that every system has, which is CPT. Right? Every quantum field theory, in particular the 2D quantum field theory that we're talking about, has CPT. So we could do that. What is CPT? This is a Euclidean picture. CPT in Euclidean signature is just a 180-degree rotation. Right? It's part of the Lorentz group. So if I combine CPT with the Z2 transformation, it actually preserves this picture. But it acts in an orientation reversing fashion on the defect because it switches because it rotates one of the transverse directions. Thus, we can think of this operation as a T-symmetry on the defect. Okay, so we've learned an interesting thing. This is actually true in every space-time dimension. So in every space-time dimension, if you have a Z2 unitary symmetry, then the theory on the defect has time reversal symmetry. Okay, now if you have time reversal symmetry, so if we have time reversal symmetry, we can look at the ground states. And these can either be one of two things. They can either be a singlet under T, or they can be Kramer's doublet. Okay, so the meaning of this anomaly, and again, there's some math to chase through to check that this is right, but when this anomaly is off, you're in this case. When it's on, you're in this case. So the bulk system, has a Z2 anomaly, means that the theory, the quantum mechanics on the defect has Kramer's doublet ground states.
This is the same previous mechanism that we discussed? No, sorry.
No, this is the same. Yeah, this is the same because once you're in quantum mechanics and you have, I didn't do anti-unitary symmetry, but it's the same. Kramer's doublet for T symmetry is a projective representation of T.
But you said Z2 doesn't have relative.
No, but this is not Z2. This is T. Anti-unitary Z2 does. It's important. Anti-unitary Z, then there's a meaningful phase in T squared. Right. So okay. So this is an example of what it means. So the bulk system doesn't have any projective representation, anything like that. But we see that we can detect the physical meaning of this anomaly by looking at the world volume theory of this defect, this quantum mechanics, and asking what's going on with this inherited symmetry. Okay. So we're out of time, but so I'll just flash for you that an example system is the 2D CP1 sigma model with with the reflection symmetry on the sphere. So there's an orientation reversing symmetry on the sphere. That's a Z2 unitary symmetry. So on the target space, it's reflection. And that 2D theory has this anomaly. Okay, so it actually occurs in real simple systems that you care about.
And sorry, just to understand, so depending on the field theory on CP1, you...
Here I'm just talking about the 2D CP1 sigma model target
sigma,
space.
okay,
Just literally that field theory.
Okay, okay.
That vanilla field theory has
Okay,
this anomaly.
I see.
Yeah.
I see. Interesting.
So if you were to think of this junction as being inserting a point on the quantum mechanics defect, so as a defect on the quantum mechanical line, then this type of manipulation that we did essentially amounts to the same type of manipulation if I look at one particular line.
Mm-hmm. Yeah, exactly. Yeah.
And the Z2 symmetry is just complex conjugation on the CP1.
The Z2 symmetry, it's the is that complex conjugation? It's the two. So we have the two sphere, and it has an O3 symmetry.
Yes.
So it's the element that's not in SO3 that I'm talking about.
Got it.
Yeah. Okay.
Thank you.